This week we're going to be focusing on tasks and validation. And what that means is that we need to understand what it is that people want to do with visualizations and then decide if a visualization is good or bad. And so I want to start with just a practical example, which I think is a classic one that shows just how bad or good different visualizations can be. And this is based on the Space Shuttle Challenger explosion from 1986. I judged myself as getting old when I had students who no longer remembered this happening. I was really early in elementary school when this happened, but everybody in the US who is in elementary school watched this because one of the things they did in this shuttle mission is that they had this nationwide search for an elementary school teacher to be a member of the shuttle crew. She spent a year training as an astronaut, and she was going to go up and teach all these lessons and do all of this school stuff as part of the mission. So all the elementary schools in the country watched this live because there was a teacher going up, and a lot of students, especially those a little bit older than me, this is kind of their first major memory. I do remember watching this in school, and of course it didn't end well. What I want to do is show you just the 2-minute video of the Challenger takeoff and explosion itself, and then we're going to come back and actually deconstruct what happened.
And liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Now control. Roger, roll, Challenger. Good roll program confirmed. Challenger now heading downrange. Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles, downrange distance 3 nautical miles.
So the 25th Space Shuttle mission is now on the way after more delays than NASA cares to count. This morning it looked as though they were not going to be able to get off.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
Looks like a couple of the solid rocket boosters blew away from the side of the shuttle in an explosion.
Flight controllers here looking very carefully at the situation. Obviously a major malfunction.
Okay, so what does visualization have to do with this? There was a long investigation, obviously, that followed the explosion, and what they found was that the solid rocket boosters, which are the pair of rockets on the outside that you saw kind of shooting off at the end, they had failed, and it was because they are connected in segments. There are rubber rings between those segments called O-rings, and one of those had failed and essentially allowed the rocket fuel to catch fire from the outside, and it exploded. This was a risk that NASA sort of knew about. They had had issues with the O-rings leaking or cracking or having some kind of issue before, and the company that manufactured the rockets had kept track of this. This, what we're looking at here, is the visualization that NASA and the rocket company had available to it that was used on the day of the Challenger launch to decide whether or not to go. And we kind of thought that the outside temperature had something to do with failure rates in the O-rings. And so what we can see here is that on the x-axis you have numbers in A and B. Each of these numbers refers to a different shuttle mission. And then A and B is rocket A and rocket B. So you can see every shuttle mission has 2 rockets shown. The temperature at the time of launch is shown in the upper left of the rocket A. And then if there's damage, it's marked with the ring that had the damage and then a little indicator that's showing the kind of damage. So we can see that this is erosion, it's shown with an E. Here, heating of primary O-ring is shown with an H. And so the letter and a little indicator marks what's going on. All right, is there a connection between temperature outside and the severity of the damage that happens to the O-rings? That's the question, because it was quite cold on the day of the launch and they wanted to make sure it was safe. Well, it's a little hard to tell. I mean, here it's 57, which is pretty cold, and there was some damage. Here it was 53 and there was some. But we also have damage when it's 70, when it's 70, when it's 75, and again at 58. So it's kind of hard to tell. Edward Tufte used this as an example in his book, and what he did is take the same data and plot it in a different way. So the question that we're trying to ask here is, what's the relationship between temperature and damage, and specifically, should we launch the shuttle today? Here's his redrawn version of that data. So we have dots indicating the O-ring damage, we have temperature on the x-axis, and we have severity of the damage. And what we can see is that there's not a ton of damage. We're in the warmer temperatures, though there is this outlier up here. But as it gets colder, the damage and the severity of the damage gets higher. And when we launched the Space Shuttle Challenger, it was 31 degrees, which was extremely cold. This is in Florida. It's almost never that cold. But if you actually fit a line to this data, you can see that we get this really extreme expectation of damage here, which is what happened. And so if you can visualize the data in a different way, it allows you to make more informed visual decisions. And even if we left this point off, if we're just looking at the data over here, we can kind of see the trend towards more severe damage when it's colder. We don't have any safe launches once we get below 65 degrees. So this highlights the need to create visualizations that support the tasks and the questions that are at hand. And then what we also want to be able to do is compare visualizations. So if I ask you, is this one that we're looking at better than the original? I think now we can say yes, because it makes it easier to visually make that decision about whether or not we should launch. What we're going to talk about this week is how do we actually compare visualizations and decide that one is better than the other. What that ultimately comes down to is, do they do a better job of supporting the task that the user has at hand? So we're going to break up the content that we look at this week into first understanding what tasks are, what are people trying to do, what are the questions they're trying to answer, and then once we know what the tasks are, how do we actually evaluate visualizations?